In this video, we are going to learn about universal gates. What are these universal gates? We all know that three basic gates are OR, AND, and NOT. Correct? So, these three logic gates usually are used together to build any logic circuit for any Boolean expression. But there are two gates called NAND and NOR, which are called universal gates. Okay, why are they called so? These universal gates means these two gates can be used to implement any given logic circuit. This is called universal gate. Okay, so this also can be used to perform functions of any of the basic logic gates. Okay, that means these NAND and NOR can be used to implement these three functions also. So now let us see what these gates are specifically and how they can be used to replicate these basic logic gates. Okay, let us start with NAND gate. NAND gate means basically not and. Okay, so the truth table of this can be implemented by complementing the AND gate, which means NAND gate is a two or more input logic gate with one output for which the truth table can be obtained by complementing AND gate. Okay, what is the logic for AND gate? If both inputs are, of all inputs are high, then output will be high. In other case, it is low. That is AND gate's condition. So now here for complementing AND means except in this case, remaining all cases are high. Okay, now let us see how it is represented. The logic circuit can be represented like AND gate with a NOT gate like this, which also can be represented as this A, B, Y. The expression for this NAND gate can be written as y equal to a dot b whole bar, where a dot b is AND gate and it is not of AND gate, so we have represented it with a bar. So this is the expression. Now let us see how this can be realized in a truth table. A, B, Y. Since there are two variables, we have four inputs. Okay, so except for this case where all inputs are high, the output will be high. That will be the AND case. So except that way, so here this will be 0, remaining all cases will be 1. So this will be a pure complement of AND gate. Now we have understood what an AND gate is. Let us try to understand what a NOR gate is. What is NOR gate? NOR means as similar to NAND, since it is an not of AND, here it is not of OR. Okay, NOR gate is a two or more input and one output logic gate, which is a complement of OR gate. Now let us see what is the condition for OR gate. The condition for OR gate is in where all the inputs are low. If all the inputs are low, then output will be low. That is the OR gate condition. Okay. So now let us try to understand. If it is a complement of this, then OR gate condition will be high in this scenario. Now, NOR gate can be represented as not of OR gate, or this can also be represented like this. The expression for OR gate is A plus B whole bar, where A plus B or A or B refers to OR function and it is a complement, so the bar. Okay, now let us realize its truth table. Since we have two variables, there are four combinations. So except in this case, that means here it is high, remaining all it is low. So this is how NOR gate is realized. Now we also have one more gate which is a special one. Now let us see what that gate is. It is XNOR gate. This XNOR means exclusive NOR. Okay. So what does it say here? It is complement of XNOR, means it is not XOR. Here this is complement of XOR gate. Okay, what is the condition for this XOR? If the inputs are different, then output is high. That is XOR. That means the complement of this. Other than this case, this will be high. Okay, so XNOR can be represented as this with a NOT gate. This also can be represented as this, where A, P, Y. The expression for XNOR will be this. Okay. Now let us realize its truth table. A, B, Y. 0, 0, 0, 1, 1, 0, 1, 1. Here output will be high if the inputs are different. So this is opposite of that. So here output will be high when the inputs are same. So only these two scenarios we have. Remaining cases will be 0. So this is how XNOR gate can be realized. But now in our first slide we have understood these NAND and NOR are called universal gates. Now let us see if we can realize any of these gates, any of these basic logic gates, or and not using this NAND or NOR. Okay, now let us see that part. So using NOR gate, let us realize all the three now. First, using NOR gate, let us realize NOT gate. Okay, to realize a NOT gate, this is the NOR gate, correct? We all know this is the symbol for NOR gate. Now, to make it as a NOT gate, we are shorting its both inputs. This is A and this is Y. Here we get Y equal to A bar, which is a NOT gate. Okay. Now let us see the other one. Using a NOR gate, how can we realize OR? So we can do this, and we are using two NOR gates here. Okay, this is A and this is B. By NOR you will be getting A plus B whole bar. To invert it, you need only A plus B. You don't need A plus B whole bar. So you are getting Y equal to A plus B in this scenario. Now let us see the AND gate realization. Now for AND gate, the expression will be y equal to a dot b, where y equal to a dot b. Now we have to get them separately. So this is NOR gate. This is one more NOR gate. So we are sorting the inputs here and giving A and B. Since this will work as a NOT, the output you will be getting will be A bar and B bar. When A bar and B bar go inside one more NOR, here it will be getting complemented and you will get y equal to a dot b. So this is how using NOR AND gate can be realized. Now let us see if by using NAND gate can we realize all these three. Okay, so let us check. NAND gate can be realized using NAND gate. NOT gate can be realized in the similar way how NOT gate is realized using NOR. We are going to sort the inputs like this and we'll get Y. It is equal to A bar. Here it is called as NOT gate. Now let us see if we can realize AND gate using NAND. Okay, so for that we will be needing AND like this, then Y equal to A dot B, where A and B are the inputs. Okay, so now finally realizing OR gate using NAND. Here also we are going to short at the input A, B. This will go to NAND and the output will be Y equal to A plus B. So this is how all the gates can be realized using NAND and NOR. That is why these are called universal gates. Now in this video, we have understood why NAND and NOR are called universal gates and what are their specific logics like NAND, NOR, and we have also learned about XNOR, which is an exclusive NOR, which is a complement of XOR. And now we have seen how each basic gate can be realized by using NOR and NAND.